Hi, in this video I'm going to work through the solution of an engineering mechanics rigid body equilibrium problem. Let's start by trying to understand the problem by looking at the diagram and reading the information that's given. So we've got here a part of a mechanism is shown to the left. So this diagram here is meant to represent part of a mechanism, the component A, B, C, D, and we've got some connections here at B and D that are supposed to represent connection to structure or another part of the mechanism. So the component that we're particularly analysing is ABCD, and we see that it's loaded by a 500 Newton metre couple at A, so we can see that over here. So let's just highlight that in our solution, in our question information. And we're also told that we've got a 650 Newton force acting at C. So we've got that here, and we can see that that acts at 30 degrees to the vertical. So let's also just highlight that in our information. And we're told that the component is connected to the rest of the system, or rest of the mechanism, which is not shown, by a pin joint at D, so up here. So we have our pin joint here, D, and we've also got a roller support at B here. So understanding these types of supports are important for when we draw our free body diagram in a minute. So let's just go over here and highlight that information. So we have a pin joint at D and a roller support at B, and we're asked to determine the magnitude of the reaction forces on the component at the supports. And we also just take note here that the dimensions shown on our diagram are in millimetres. Okay, so the first step in our rigid body equilibrium problem solving is to draw the free body diagram. So we start out by drawing just a simple representation of the external boundaries of the body we're analysing. Okay, so in this case it's a fairly simple shape that we need to draw for our free body diagram. We can then go and put on some dimensions for reference for when we're writing our equations later on. And we should also put on some labels for the points of interest, so A, B, C, D, where we have loads and support points, and we'll need those for reference when we write our equations shortly. Okay, so the next step is to start by putting in the forces and moments on our free body diagram. So start with the ones that you know. So starting with our 650 Newton force here at C, we can put that on our free body diagram. And next we also have the applied couple at A, so show that also on your free body diagram. And then we need to start to consider the connection between the component and the rest of the system, right, or the rest of the structure. So let's start by looking at this connection here, the roller support. So because this is a roller support, it's free to move in the horizontal direction. Okay, so there's no force of constraint at B, but it's constrained from moving in the vertical direction. So we need a force to represent that connection between the component A, B, C, D and the rest of the system. Okay, so down in our free body diagram here, we have just a single force in the vertical direction. And of course we need to label that. So we've just called that R for the reaction force, subscript B, because it's applied at point B. Note that when we draw our free body diagram, that we don't show on here the supports from here, right? Because what we're showing on our free body diagram is the force that this component applies to the component or the body that we're analysing. Okay, so we now need to look at point D here, where we've removed the pin support, so we need to replace that pin support with the forces that pin support applies to the component ABCD at point D. So if we go back up here to that support, it's this pin support here is fixed to ground or the rest of the system, so the component ABCD is constrained or prevented from moving in the horizontal direction, and also prevented from moving in the vertical direction. So down on our free body diagram here, we have forces to represent that, or arrows to represent those forces. And on our pin support here, it's free to rotate, so there's no moment reaction there. Okay, so the next thing we should do, of course, is to label these forces, these reaction forces. So the reaction force R at point D in the Y direction, and again R for the reaction force at point D in the X direction. And now that we've used component forces in X and Y directions, we should of course indicate what they are with respect to a coordinate system. Okay, so I've indicated over here the X direction, positive to the right, Y direction, positive upwards, and also indicated the positive direction for moments being anti-clockwise. Okay, so now that we have our free body diagram, we can go and start to write some equations of equilibrium. Now usually the best one to start with is the moment equation, because we can usually pick a point, such as point D here, where we have one or more of our unknown forces that we're trying to solve have a zero moment, so they won't appear in the moment equation. So here we have Rdy and Rdx both pass through point D, so they'll have a zero moment about point D. So the moment equation that we write, of course, will be sum of the moments about point D, anti-clockwise positive, all equal to zero. Okay, so it's very important that when you write this equation that you have this indication here for where you're taking moments about. Right? You must indicate the location for calculating the moments, right? So that you and anybody else, when they come to check your work, can see whether the equation that you've written is correct based on this indication here. Otherwise, they've just got to try and guess. And if you've got to guess, well, then you haven't done it well enough. Okay, so let's start by adding in our moment components. So we've got a 500 Newton applied couple, which is in the anti-clockwise direction, so that's positive 500. And we have a force RB here, which is at a distance of 500, perpendicular distance of 500 from point D. Okay, so its moment effect will be RB times 0.5, because we have to convert from millimeters into meters, right? Because our 500 here for our applied couple is in Newton meters. The other thing to note here is the negative sign out the front. Okay, so we're considering this force here about point D, so point D is over here. Okay, so that force pushing on this component will tend to rotate around clockwise about point D. Okay, so therefore it's negative. Alright, so then we need to take into account the moment effect of our 650 Newton force, and the easiest way to do that would be to find components. So we'll find the vertical component, which will pass through point D, so that will have no moment effect. The horizontal component, which will be 650 sine 30, acts at a distance of 400 millimeters or 0.4 meters from point D, so we can put that into our equation. So 650 sine 30 times 0.4, and all of that is equal to 0. Okay, so we can see that we end up with one equation, one unknown, which is our force reaction RB. So doing our algebra, we can find that RB is equal to 1,260 newtons. Okay, so the next thing to do is to start to use the other equations of equilibrium. So I've started by using some of the forces in the horizontal direction equals 0. And if we look at our free body diagram, we've got rdx, and the only other horizontal component or other horizontal force is the horizontal component of the 650 Newton force. So we can write that in straight away. rdx equals 650 sine 30. And that equals 325 newtons. Then next we do sum of the forces in the vertical direction equals 0. So we'll have RB in the positive direction plus the vertical component of the 650 Newton force, so 650 cos 30, and RDY in the negative direction because it's acting downwards, and all of that is equal to 0. So again, doing some algebra, we can solve for RDY, which is 1822.9 newtons. Okay, now we're not quite finished because the question asked for the magnitude of the forces at the supports. So we've got RDX and RDY components here. So we need to go and use Pythagoras rule to find the reaction, the magnitude of the reaction at D. So square root of the sum of the squares, and putting in our values that we calculated before, we get RD equals 1851.7 newtons. And finally, we should summarise our answers. So final answers at the end, and round up to an appropriate number of significant figures. So rounding up to 3 significant figures, we have RB is 1.26 kilonewtons, and RD equals 1.85 kilonewtons. Okay, so that's it for that problem. I hope that was helpful, and I'll see you next time. Thanks for listening. Bye.